Welcome to the shape of space, linear algebra. This lesson is on the dimension of a vector space. We'll define dimension, then we'll prove several theorems concerning the dimension of a finite dimensional vector space. The dimension of a vector space is defined to be the number of vectors in a basis for a vector space. However, for this to have meaning, we first need to prove that every basis for a given finite dimensional vector space has the same number of vectors, and we'll do that in this lecture. So first, we define a finite dimensional vector space as one that has a basis with only finitely many vectors. Our focus in this section will be on such vector spaces. There's also infinite dimensional vector spaces, but we're not going to talk about them in this lesson. A trivial space is a vector space with only the zero vector. The trivial vector space has dimension 0 since it has no basis. Or equivalently, the empty set is its basis since the span of the empty set is the zero vector. That's by definition. I think I mentioned that earlier. So to prove that every basis for a given finite dimensional vector space has the same number of vectors, we're going to need to prove a number of theorems. And the first one we're going to prove is on the next slide. Let's look at our first theorem in this section. We have a basis S for a vector space. We have a vector in this vector space that's a linear combination of the elements of the basis where at least one of the coefficients is not equal to 0, so v is not the zero vector. Then the theorem says we can exchange SI for v and get another basis for our vector space v. So what we need to do is show that this new set S prime that's formed from S by replacing SI with v is a basis. So we need to show it's linearly independent, which we'll show on this slide, and also that the vectors in S prime are a span for v, and we'll show that on the next slide. So take any linear combination of the vectors in S prime that is equal to 0, which I've written here, and then substitute in our expression for v here, which I've done here. So now this new expression only has terms from S. And what we do is we collect the like terms. So the S1, for example, is B1 plus BIA I. Another example is BN. SN, excuse me, that would be BN plus BI times AN. And all the terms have this general format except for the SI term, which is just BI-AI. And since the vectors in S are linearly independent, we assumed S was a basis, all the coefficients in the above expression are equal to 0, including BI-AI. But we know that AI does not equal 0, so the BI must equal 0. And then we can take that BI equals 0 and plug it back into here, and we get a lot of cancellation, including this term altogether, and we get this expression here. Although it's missing the SI term, it doesn't matter. It's still a linear combination of the basis vectors from S, and we know that since the vectors in S are linearly independent, all these B's must be equal to 0. So B sub j equals 0, j equals 1 to n. We already had shown for this particular BI is equal to 0, and then we've shown the rest of them are here. So S prime is linearly independent. To complete our proof, we need to show that S prime spans the same space as S. In other words, that it spans the vector space V. Since we know S is a basis, it follows that let me point to it here, the span of S prime is a subset of the span of S. So we just need to show the containment in the opposite direction, that the span of S is a subset of the span of S prime. So take any U in the span of S, then by definition we can write U as a linear combination of the vectors in S. Then we have from our theorem that V is a linear combination of the vectors in S, where A sub I is not equal to 0. Then we can subtract all of these terms except for the A sub I, S sub I from V, and then divide both sides by A sub I. And we get this here. So in other words, we can write S sub I as a linear combination of the vectors in S prime, essentially. We're using V here. Substituting the expression for Si into the expression for U. So substituting this into here. We have this, and then we collect terms. So we have just collecting the terms corresponding to S1, we get C1 minus Ci A1 over A sub I, and so on, all the way up to Si minus 1. These all have the same format, except for the term corresponding to V. That's just Ci over Ai V. Then continuing, we get the same format collecting the terms here. Thus, U, this generic vector that we took from the span of S, can be represented as a linear combination of the vectors in S prime, which implies the span of S is a subset of the span of S prime. And that proves that S prime is a spanning set for our vector space. And since we proved in the previous slide it was also the vectors in S prime were linearly independent, we've proven that S prime is also a basis for V. Making use of our theorem that we just proved, we can now prove the main theorem in this lecture. In a finite dimensional vector space V, every basis has the same number of elements. So to prove that, we'll start with a basis of V with a minimum number of elements. There could be more than one, but we'll start with such a basis that has a minimum number. And let T be any other basis of V. Since we assumed S has a minimum number of elements among the bases of V, we know that T has either n or more elements. What we want to show is that T necessarily has n elements. So since S is a basis, we can write T1 as a linear combination of the vectors in S. And since T sub 1 is not equal to 0, at least one of the coefficients in this linear combination, let's say corresponding to I sub 1, is not equal to 0. By theorem 13, we can exchange T sub 1 with S sub I sub 1 and form the basis S sub 1 consisting of T1 and the other elements of S except for S sub I sub 1. Let's continue with the proof on the next slide. We can repeat the same argument that we did on the previous slide, except we'll use S1 in this case. Since S1 is a basis of V, we can write T sub 2 as a linear combination of the vectors in S sub 1. And since T sub 2 doesn't equal the 0 vector, at least one of the coefficients in the linear combination is not equal to 0. Further, one of the coefficients, cannot be that only the coefficient of T sub 1 is non-zero, since that would imply that T sub 1 is dependent on T sub 2, which contradicts the assumption that T is linearly independent. We assume T was a basis, but we only need the fact that it's linearly independent here, and that we don't want to contradict that. So the coefficient of at least one of the vectors from the original basis, S, must be non-zero. Let's say that's I sub 2. Then we apply theorem 13 again, and we can exchange T sub 2 was S sub I sub 2 and formed the basis S sub 2, consisting of T sub 1, T sub 2, and the other elements of S except for the ones we replaced, S sub I sub 1 and S sub I sub 2. Then we can continue this process, slowly replacing everything in S with vectors from T, and we end up with this basis S sub n, with n vectors in it from T. At this point, we have to conclude that T cannot have more than these n vectors, because if there was another vector, T sub n plus 1, not equal to any of these, that remains, it would be in the span of S sub n, since S sub n is a basis, and hence T sub n plus 1 would be a linear combination of the other T sub I vectors, these vectors here, contradicting that T is linearly independent. So we've proven that T must have exactly n vectors. Theorem 15. A linearly independent set T of vectors in a vector space V cannot have more elements than the dimension of V. This follows from the proof of Theorem 14. If you look at it closely, you'll notice that although we assumed T was a basis, we only used the fact that it was linearly independent in the proof. So that pretty much means that our proof of Theorem 14 applies here, and we cannot have more than elements than the dimension of V for our linear independent set T. Another theorem we have is any linearly independent set S in a vector space can be expanded to form a basis for V. So we have two cases. If S also spans V, then we're done, since S would be a basis, so that's not particularly interesting. But assume S does not span V, then from Theorem 9, from several lectures back, let me just review Theorem 9 again. I have it listed here for your refresh your memory. But given a linearly independent set S in a vector space V and a vector V not an S, the set S union V is linearly independent if and only if V is not in the span of S. So making use of that theorem, adding a vector to S that is not in the span of S will preserve linear independence, so we can just keep adding vectors until the resulting set spans all of V. And by Theorem 15, or theorem we just mentioned up here, the adding process necessarily stops after a finite number of steps. In contrast to Theorem 16, we can have a spanning set that we can, if it's not already a basis, we can reduce to a basis by removing vectors, and that's what we have in this Theorem 17. There's three cases. Let me look at the kind of the typical case, which is case number 3 first. S contains a non-zero vector called S1. If the set S1 containing S1 spans V, then we're done. If not, then there's an S2 in our set S, such that S2 is not in the span of S1. And then by Theorem 9, which we talked about in the previous, or we refreshed our memory just recently in the previous slides, the span of S1, S2 is linearly independent. If that span of S1 and S2 equals V, then we're done. Otherwise, we continue adding vectors until we span all of V and thus form a basis for V using the vectors from our set S. And this process must stop since we assumed V is a finite dimensional vector space. So this is kind of the typical case where we have a set S. It spans all of our vector space, and we just start with one of the vectors. If it spans the vector space, we're done. If it's not, we go to another vector from the set S that's not spanned by the initial vector, and that's linearly independent by our Theorem 9. And then if that spans all of V, we're done. Otherwise, we add another vector from S and so on. Now we have two kind of odd cases here, but I'll mention them for completeness. In one case, if S is the empty set, then the empty set spans the zero vector space, this set here, because the span of the empty set is defined as such. The empty set is also linearly independent vacuously, since there's no vector to form a non-trivial linear combination. Thus, the empty set is already a basis for the zero vector space. Then the second case is where our set S contains just the zero vector. The set containing the zero vector spans the set containing this set here with only the zero vector in it, since the span of the set with a zero vector is the set with a zero vector, right? It's just all multiples of the zero vector. However, the zero vector is linearly dependent because you can take a multiple 1 times 0 and get the zero vector, and that's a non-trivial linear combination yielding the zero vector. So in order to reduce S to a basis, what we do is we remove the zero vector from S, leaving the empty set, and that does in fact form a basis for the set containing the zero vector. That's by definition and what we just discussed in case number 1. So these cases are a little bit befuddling, but they're here for completeness, and they're based on this what seems to be a strange definition for the span of the empty set being the zero vector, but the span of the zero vector doesn't give us a basis because it's not linearly dependent. So we actually have to remove a vector to get back to a basis, which is a bit strange, but that's how the definitions work here. We have one last theorem for this lesson. In an n-dimensional vector space V, a set of n vectors is linearly independent if and only if S spans V. So going in the forward direction, since we have if and only if, we need to go both directions. If S is a set of n linearly independent vectors, then by theorem 16 it can be expanded to be a basis for V. This implies V has a basis with more than n vectors, which contradicts theorem 14, which I listed down here just as a reminder. Thus, no expansion of S is needed for S to span V. In other words, S spans V. So that goes in one direction. Then going the other direction, if S spans V and is linearly dependent, then it can be reduced by theorem 17 to a basis for V. This implies there is a basis for V with less than n vectors, which contradicts theorem 14. Thus, if S spans V, it must be linearly independent. Okay, so that's it for this lesson. I have quite a few more lessons coming, so stay tuned.